Okay, I'm going to be talking about some incredibly weird, or at least unfamiliar stuff. So if at any point you feel lost or you want me to repeat something, please just raise your hand virtually in the Teams question, and I'll be happy to backtrack. One of the big advantages of an online presentation over reading a book or an article is that you can ask me questions at any time, so I hope you will. There's a big gap between like hand-wavy but wrong descriptions and correct but impenetrable to non-experts documents, and marketing in the subject of quantum computing is designed to mislead. So I hope that by the end of this presentation, you will at least have an idea of what quantum computing is and what's coming down the road. So my name's Craig Stuntz. I work for Improving, and you can get the entire deck for this talk at speakerdeck.com/CraigStuntz, as well as copies of decks for my other presentations. And I would recommend you do that because I have citations for nearly all the material in this talk that are on the slides. So if I talk about something and you find it interesting and you want to learn more, you can go to the URLs from the slides, and if you just grab the deck at speakerdeck.com/CraigStuntz, that'll make it real easy to look up those links. So I want to start out by just asking you, like, what's the hardest problem that you can think of to ask a computer to solve? So if I just like list some difficult problems off the top of my head, there's like Bitcoin mining, which says that for some value, I have to figure out which value is the SHA. If I take the SHA 256 of that value, what value? I'm using the word value a lot, but what value can I take the SHA 256 hash of to get a given value? And that turns out to be quite hard. And then we know about RSA encryption, where I have a very large number, and I know that it's the product of two very large primes, and I need to figure out what the two primes are to break the encryption. The graph isomorphism problem is a problem from theoretical computer science that actually shows up in lots and lots of different places. And that just says, are two graphs that maybe are twisted or pulled around a little the same? And that turns out to be very difficult for very large graphs. You might have heard of the Netflix problem. There was a contest maybe 10 years ago that said, and this goes back to something from machine learning called collaborative filtering, which is given a small number of ratings. So if I'm a Netflix user and I sign up and then I rate a few films, and then I have a much larger number of ratings that are made by other users, can you suggest movies that the first user would enjoy? And it's not so hard with a very low level of accuracy, but doing it with high accuracy can be very challenging. But the most difficult problem I can imagine solving on a computer is creating a new React app. You could let it go until the heat death of the universe and it would still be filling your file system with files. But the really, really interesting part of this is that we don't actually know how hard these problems are. And this is one of the big ideas I want you to take away from the talk. It's probably the biggest problem in theoretical computer science today. You might have heard of it as the P versus NP problem. Some would say it's one of the biggest philosophical problems that humanity has to face. And it's basically P and NP are two groups of problems with, we think, different computational complexities. There are many other groups of problems, but P and NP are the ones that get the most attention. And the question is, are they actually different? Does one of these groups contain harder problems than another one? We don't know the answer to that. And if you can prove that P is equal to NP or P is not equal to NP, you actually win $1 million prize. It's considered so important, there's $1 million prize on the resolution of the question. And so I'm just going to be going back and forth between this notion of there are a lot of problems that we don't know how hard they are, and then quantum computers can solve certain problems that today are very difficult to solve, and they can solve them efficiently. So what is the promise? Why would anybody care about quantum computers at all? Well, not to put too fine a point on it, but we think they can do interesting things. So we think that they can break RSA encryption, and actually not just RSA, but lots of different kinds of encryption. More constructively, there are processes in nature that appear to be inherently quantum mechanical. And if we want to simulate these processes efficiently, it helps to have a quantum computer. The equations of quantum mechanics prescribe a way to calculate properties such as stability and chemical reactivity of a molecule like a drug. But these equations cannot be solved classically without making lots of simplifications. So with a quantum computer, we could better figure out how to do certain chemical reactions or make drugs that do things that we need, and that's obviously very useful. There's also good reason to believe that quantum computers may provide an exponential speed up on certain calculations commonly used in training machine learning models. And actually, this is kind of a complete list. There are one or two other things here, but this is Scott Aronson's list of things that quantum computers can do, or at least things that they can do faster than the classical computer. So simulate quantum physics, break public key cryptography, combinatorial search and optimization. I'll talk about that a little bit later in the presentation. They might be able to do machine learning faster, and you can use them as a prover to prove beyond classical capabilities. And right now, that is what we know that quantum computers can do well. It doesn't seem like a very long list, but there are a couple in there that are considered so important that people are pouring millions of dollars into research to build bigger and faster quantum computers. However, TLS doesn't seem to be broken, and that's because the quantum computers that we've built right now are pretty small in terms of their computational capabilities. You can use them to factor numbers like 15 and 21, which is obviously not useful for breaking encryption. And quantum supremacy is maybe not yet shown, which means that the classical simulations of quantum computers appear at this point to be mostly faster than running things on a quantum computer properly. I hesitate on this. I say maybe not yet shown. Google has claimed quantum supremacy on an algorithm that does a kind of a useless thing. Some of the other people in the market disagree with that. So 2020 might be the year that, or 2019 might be the year that quantum supremacy happened, or it might not. We're really not sure yet. And it's in part because we haven't done anything super useful with the quantum computer yet. Classical algorithms and hardware keep getting better. So, you know, if I say that quantum supremacy means building a quantum computer that is faster than any classical hardware can simulate, well, classical hardware is not standing still. People keep making faster and faster classical hardware. So the quantum computer has to be getting faster at the same time in order to be faster than the classical hardware. And, you know, I showed you the complete list of what a quantum computer can do, we think faster than a classical computer. It's a pretty short list, so it's not like when we build this thing that all of our computations magically get faster. There are a few things that we think they do well, and for the most part, classical computers are still going to be how we do our computations. The theoretical advantages of quantum computers are not well understood. And many popular articles on quantum computing are mostly marketing, okay? So, but I'm gonna say you should care anyway, because of the things that quantum computers can do well, there are some things that are just monumentally important. In particular, cryptography. So public key cryptography was invented, we think, in 1977. It may have been invented earlier by government agencies who just didn't talk about it. RSA encryption was invented in 1988. PGP debuted in 1991, and SSLv2 in 1995. So it takes 1 to 2 decades to go from inventing a cryptosystem to feeling confident enough about it that we will do business with that cryptosystem. So we need to, if we think that quantum computers are coming in 10 or 20 years that can break public key encryption, we need to come up with new cryptosystems now so that we have the time to vet those cryptosystems and feel confident about them when we need to use them. Also, all computation, all computing, all chips rely on quantum effects to some extent. If we understand these better, we have the better capability to build new hardware, even if it's classical hardware. Some theorists think that quantum computers are impossible, and if those people are right, this notion probably also requires new physics. So either way, we learn something. So I've already been using this term classical computing for a few times now, and I'm going to be using it again in the future, so let me be a little bit more specific about what it means. This is the kind of computation done by the computer you're using right now to watch this presentation. It is a model of computation that's so ubiquitous, we sometimes forget that there are other models. It uses registers and binary logical operations on those registers, such as add or and. But there are other models of computation, and there are many of them that do exist, such as analog computers, biological computation, and quantum computers. And these are just fundamentally different kinds of computers that work in different ways and have different capabilities. So we're going to talk about one specific kind of computation, which is a quantum computer, but we should remember there are many kinds. So when you read about quantum computing, you're pretty quickly confronted with a lot of math and physics. All the books you can get about quantum computing now start with linear algebra and kind of go deeper as you go. And or at least once you've stripped away the marketing filler. I mean, there are the magazine articles that say nothing. And you might think, like, how much of this do you need to know? Because, like, as a working programmer, you don't necessarily need to know like a lot of math and assembly. You can lean on a compiler and get a lot of work done without having to know a lot about how the CPU actually works. So what you need to know about quantum computing, it kind of depends on who you are. If you're a hardware designer, these folks need to know all of the math and all of the physics. But as a library author or a cryptographer, you just need to know most of the math. And then as a programmer, I would argue you really don't need to understand very much about quantum computing if all you want to do is like call out to a library, okay? So you need to know some characteristics of the performance and what it's good at, but I would argue, you know, you don't really need a lot of the linear algebra because you really just need to understand the performance characteristics of a quantum computer in order to decide whether or not you need to use it. So to that extent, we often think of our computers as being general purpose, but in fact, they contain a number of special purpose devices like a GPU, perhaps a tensor processing unit, or a digital signal processor, okay? And like when I bought my first computer, and this gives you some clue as to how old I am, it was an 80286, and later I went out and bought an 80287 math coprocessor, which I could plug into a slot next to the 80286, and that made my Excel sheets fill faster. But one way that you can think of quantum computing hardware is as a coprocessor for certain kinds of tasks that quantum computers do well. Quantum computers, at least today, are not general purpose, and you need a classical computer to prepare for the quantum computation, and then later on to get the results back. Also, they tend to be located in data centers. You're unlikely to have one on your phone anytime soon because they tend to run at very cold temperatures. And by cold, I don't mean like freezer cold, I mean close to absolute zero. And you need a room-sized refrigerator to cool the quantum computer. It will be a while before we develop one that is going to run, you know, on a phone or even a laptop or desktop computer. There's a lot of technical problems to solve. So today, anyway, they're likely to be in the cloud. So, in fact, as the overall increase in transistor density and clock speed of CPUs seems to be tapering off, there's fairly good reason to believe that a shift from general purpose computing devices to application-specific accelerators may be the wave of the near future in hardware design. So already there are things like in Azure, you can run, you know, on machine learning specific hardware. And there's, you know, hardware for digital signal processing for things like audio and video processing. So one of the things that we already see today is specific classical hardware for specific tasks and less of an emphasis on the general purpose GPU or CPU. Okay, so I want to talk a little bit about the nuts and bolts and talk about how quantum computers work. But before I do that, I'm going to take a little time just for the sake of comparison to talk about classical computers. This is a very coarse model of a classical computer. There's a lot of details omitted here, but the important part here is the register and the combinatorial logic. This is at the heart of the classical model of computation. Programmers don't normally work at this level because compilers do it for us, but you know, we can. You can write assembly code, and this is the level that you need to think of in terms of quantum computing today, because this is the level that it changes, and this is the level that you'll be working at if you use like IBM System Q or Microsoft Q Sharp to program a quantum computer. It's very close to assembly level. So a classical computer register is kind of like the switch here. It's a bunch of bits that are all either on or off. And you probably have lots of these in your CPU, and you can set them to some value and then run an operation on them like and you'll get the value out of that operation in still more registers. So a quantum computer is going to look somewhat similar. So here I'm talking about a particular type of quantum computer known as a quantum gate array. There are other architectures under development, but this one's fairly similar to a classical computer, so it's a good entry point into understanding quantum computers. The input and the output are classical computers, and then instead of registers, we have qubits, and instead of combinatorial logic, we have quantum gates. And then instead of writing assembly, we build circuits. And again, programmers, you would think would not normally work at this level because compilers will eventually do it for us. I mean, presumably even in the quantum world. But today, the languages that we have to program quantum computers are all at this level of putting gates together. And like a register, qubits represent both the input and the output of the quantum operation and the input and the output of the quantum gates. So, but unlike a register, instead of having discrete values of 0 or 1, the qubits have a property called amplitude, which is similar to the probability that they have some value. So we're not sure which value they have, and there's no hidden state to know, but we do know the probability that it's one or the other, and we can also set the probability. So we might, as the input to our quantum algorithm, set qubits to have the probability of 100% that it's one, and another qubit to have the probability of 100% that it's zero. And then when we run the quantum algorithm through the quantum gates, we get another set of qubits out that will have the probability, you know, it might be 50-50 that it's either 0 or 1. And when we measure the qubit, it will turn out to have a single value, 0 or 1. But it will be according to the probability that we discussed. So if the probability is 50-50, the value we measure will be random, 0 or 1. So since the inputs to the quantum operation are not necessarily fixed or discrete values, but something like a probability, what's the output? Well, it's also a probability. And you can roughly think of this as a collection of possible answers, except locked in a safe. When we open the safe and look inside, we get exactly one of these results selected randomly. When we measure the state of qubits by reading them, they're no longer in a quantum state. Instead, we read out a single value, which is a randomly selected result to the problem based on one possible configuration of the inputs. Now, this seems sort of useless because if we just pick an answer at random, it might not be the correct answer to our problem. What we want to do is we want to increase the probability of selecting the correct answer. And I know that's a little vague, so we're going to give a more specific example. We're going to start with a qubit with 100% probability of being 0. After the quantum operation, the probability of being 0 or 1 is equal. It's a coin toss in this case. When we measure the output, the quantum state collapses to some value, which is maybe 1. And so, like, in terms of breaking encryption, this probably sounds totally useless, but I want to just make sure that you're with me so far and make sure that what you see on the screen makes sense. And if it doesn't make sense, I'd like you to pipe up in chat and ask questions, because what we're going to do now is we're going to take this notion of an output of a certain probability collapsing to one specific value, and we're going to talk about how that gets us to actually solving real problems. So let's start with a cartoon. I've included cartoon panels in my slides in the past, but this is the first time I've used one because it's the single most clear and concise explanation of a technical topic I could find. This is the essence of why quantum computers have the potential to be so fast, and this also explains why programming them at a low level is so unfamiliar. In quantum computing, the whole idea is just to choreograph a pattern of interference where the paths leading to each wrong answer interfere destructively and cancel out, while the paths leading to the right answer reinforce each other. And I'm going to dig into that a little bit and explain a little bit more how it works. So you may be familiar with noise canceling headphones, mixing together waves so that wrong answers cancel themselves out. Very different from how classical computers work, but it's something many of us have experienced in the macroscopic world. For example, adding noise canceling headphones work by adding extra noise to existing noise. And if you think of quantum interference of two qubits is analogous to two waves in the ocean intersecting, then the goals of the quantum algorithm designer is to make the two interfere in such a way that the correct answers are amplified and the incorrect answers are attenuated. This will greatly increase the chance that when we measure the system, we'll read out a correct answer, which we can classically verify. So the output of a quantum computation is probably correct if we didn't experience a lot of noise in the computation, So we need to verify it. And if you think about like breaking encryption, well, we know that multiplying two numbers is really easy. So if we factor the product of a large prime into candidates for its factors, we can classically multiply them together and ensure that they produce the value that we were given originally. So we may have to try the quantum computation again if we didn't get the correct answer because of noise or because of probabilities. So an analogy for this is when you kick in time on a swing, you create a resonance and swing higher. And when you kick off time, you dampen the swing. So waves and their ability to amplify each other with constructive interference or interfere with each other with destructive interference are at the heart of quantum physics. So noise is something that happens in classical computers. We have cosmic rays that come and they screw up our classical computations, and also transistors that are very small, smaller than 7 nanometers, are going to experience quantum tunneling through the gate oxide layer and possibly come up with the wrong value. But we've gotten pretty good at making classical hardware more reliable with redundancy as well as hardware, software, noise correction. We have a similar issue with quantum computers. You remember I said they typically have to be kept very cold, close to absolute zero. And this is because heat, if heat gets into the system, it can knock the qubits out of their desired quantum state. And this is like one of the ways that noise happens in a quantum computation. And the quantum computations tend to be pretty noisy. A real-world quantum computer might have anywhere from like 1 to 5% noise in its computations. So that's a problem. And one of the ways that people try to solve this problem is by distinguishing physical and logical qubits. So a physical qubit is one quantum element that can be in a certain quantum state, and a logical qubit is a combination of physical qubits that behave as a single qubit for the purpose of implementing a computation. The number of logical qubits is typically much smaller than the number of physical qubits. So this is one of the reasons that we haven't been able to do very large computations on a quantum computer yet. So I'm going to talk about computational complexity. P and NP are the complexity classes that a lot of people have heard about, but there are lots and lots of other classes in theoretical computer science, and this is a map of lots of them. So what is a hard problem, actually? So complexity theorists study how hard certain problems in computing are and try to find the limits on how efficient an as yet unknown algorithm can be. Some of them we know to be impossible. So in complexity theory, a problem is hard if the time to solve it increases exponentially with the number of inputs. And we care about many of these problems, like Sudoku and protein folding and Battleship and Free Cell, Mastermind, Minesweeper, creating crossword puzzles. These are all problems that have been studied from a complexity theoretic point of view. And some problems we know are impossible. The Entscheidungs problem, if you think back to Alan Turing, he proved that given some computation, there's no way to write a function that will look at an arbitrary computation and determine if that computation will stop or not. We know that that's just entirely impossible. Other times the solution exists but is exponentially difficult. So the traveling salesman problem says, given a traveling salesman who has to visit a number of different cities, what's the most efficient way to get from one city to the next and to go to all the cities in the set? And this becomes exponentially more difficult as the number of cities increases. And then other problems still, we know that efficient solutions exist, like the greatest common divisor. But there are a whole lot of problems that we're actually not sure how hard they are. So for example, finding products of large prime numbers. We think that this is a difficult problem because we've been working on it for centuries, actually. And certainly we have not been able to find a solution to it in spite of a lot of hard work. But we don't know that. And the weird thing is that sometimes problems that we think are hard, the next day somebody comes along and says, actually, this is not that hard. So an example is the Netflix problem. The recommendation problem, it relates to collaborative filtering and machine learning, and you've seen it in action, companies like Netflix and Amazon and others, and you've probably noticed it doesn't work very well. It's hard to do this well on classical hardware, or is it? In 2016, someone came up with a quantum solution to the problem that offered this huge speed up versus the existing classical algorithm. But only 2 years later, an 18-year-old, while trying to prove that an efficient classical algorithm could not exist, found one. And he was inspired by the quantum algorithm, and possibly he couldn't have found the classical algorithm without that inspiration. So the point here is that the line between what classical computers can do efficiently and what quantum computers can improve on is not all that clear, is changing from day to day, and we're still going to learn quite a lot going forward. So I talked about the problems in P and NP. There's this other complexity class called BQP, which is bounded error quantum polynomial time. And these are problems that the definition of the class is problems that can be solved by a real world quantum computer easily. And the problem is that we're not sure which problems are in it. And this is something that theoretical computer scientists say a lot. Okay, so I've talked a little bit. Yes.
We had a question that kind of relates here or whatnot, and I know that you had brought up a slide a minute ago that kind of talked about these classes. And so somebody had posted a thing that in there is, you know, are there actual courses right now on quantum computing that are being taught in colleges, or is it more of a kind of on-the-job training, find the information yourself?
So I don't actually know that. Certainly there are online courses you can take. I would imagine that, you know, when you look at the research that's being done here, a lot of this stuff is coming out of industry. So companies like Honeywell and Google and Rigetti and IBM and Microsoft are all working on quantum computers, but there is some university level work. So I do know that there are like graduate programs that are doing work on quantum computers. I would have to imagine there are college courses available, but I don't actually know the answer to that.
Okay, thank you.
Sure. So I want to look at how you might build a quantum computer and what they're good at, and then I'm going to talk a little bit about how to program one. And what a quantum computer does very well is a Fourier transformation. And this is something that we do in the classical world a lot too. If you think about taking a wave, like maybe the sound of a musical instrument, this will have a fundamental value, which is the note that you're playing, and also a lot of overtones. And these are like higher pitched tones that give the instrument its characteristic sound. And what a Fourier transform does is it takes that wave from the instrument and it pulls out the fundamental and all the overtones, okay? Now, a quantum computer does a very similar thing, although it doesn't just work with musical notes, it works with the output of arbitrary functions, and it can sort of decompose these into their values of the fundamental and overtones. So if you remember, I talked about how we want to use interference to, we want to make the interference such that the correct answers are amplified and the incorrect answers are attenuated, the ability of a quantum computer to pull out the frequencies that go into those correct answers is what makes the algorithm work. So the era that we're in now is been termed by John Preskill the NISQ era, which is noisy intermediate scale quantum computation, which is to say we have quantum computers that are very small in their number of qubits. They're very noisy, and you know, in order to do really useful computations, we're going to have to build bigger ones, but that is in some ways an engineering problem. So I've talked a little bit about what qubits do, but how might you build one? One way is you suspend an ion or a charged particle in free space. And in this case, a qubit is based on the electronic states of each ion, such as ground state versus excited state. You can get commercial hardware available from a company called IonQ. It claims to support 160 qubits, but full quantum computations have been demonstrated on like 30 or so entangled qubits so far. Still really impressive, but not enough to demonstrate quantum supremacy. And then another system is qubits based on superconducting circuits, for example, the amount of magnetic flux in a superconducting loop. This is used by IBM, Google, Rigetti, and others. Real hardware does exist. You can go on the IBM cloud, or actually the Microsoft cloud offers this as well. But it's noisy and the qubit counts are fairly low. Then another technology is based on superconducting wires, and this one is not the architecture I've discussed so far. So this is, instead of quantum gates, it uses a fixed structure to solve satisfiability problems. And this is, there's a company called D-Wave that makes these things. And they'll sell you a computer with 512 qubits, which sounds really impressive. But from that number alone, you'd think they would have demonstrated quantum supremacy. But there's no experimental evidence for these computers outperforming classical computers. And it's certainly a less flexible model for quantum computation. The last physical implementation of a quantum computer I'm going to discuss is called a topological qubit. This is something that Microsoft Research is working on, and this gets very weird because what Microsoft wants to do is encode its qubits in a quasi-particle, which is a particle-like object that emerges from the interactions inside matter. And a lot of physicists are not even sure that the particular quasi-particles that Microsoft is working with actually exist. These are called non-abelian anyons. Needless to say, there is no hardware yet. This is very much still in the lab. But the advantage of this, if it did work, is that they would be very low noise and low error. So you remember I talked before about physical versus logical qubits and having to combine several physical qubits into a logical qubit. That would not be necessary with a topological qubit should it exist. But this is very much still in the lab right now. So what does programming these things look like? Q# is Microsoft Research's language for expressing quantum computations. You execute Q# programs by wrapping them in a C# harness representing the classical input and output of the quantum computation. So here we set 2 qubits in initial states, and then we execute 2 quantum gates, a Hadamard gate, which is represented as H, and a C0 gate. And then we measure the results with M, and then we act on the measured results. So this code is not that hard to read, but it's not at all obvious what's going on here. Like, what do these 2 quantum operations do? And this is just a demonstration of a Bell state. which is sort of interesting if you care about quantum physics, but it's not particularly interesting as a computation. It's like I just demonstrated an adder circuit. And the point is we're working at a level here which is possibly interesting to microcode library designers, but maybe not really yet interesting to programmers. And a lot of work is needed in order to use this to solve real business problems. So about that crypto thing. First, I want to use this statement from Scott Aronson to correct a misimpression that a lot of people have. It's a really important point. Quantum computers would not solve hard search problems instantaneously by simply trying all the possible solutions at once. That is not what they do. We noted before that quantum computations don't search discrete possibilities, but instead are engineered to increase the probability that when you measure the state of the qubits, you'll find the correct answer. So how does that work? Let's look at Shor's algorithm, which breaks RSA encryption. So first we need to talk about how RSA works, and I'm going to just give you a whirlwind tour of RSA. Given two numbers, it's easy to find their product. You just multiply them together. But if I gave you the number 221 and asked you to find the prime factors, this would be challenging for a lot of us, even if we can do multiplication in our head. But if I told you that they're 13 times 17, you could pretty easily verify that that, in fact, comes out to 221. So very roughly speaking, we can give away the product as the public key without revealing the prime factors, which are the secret key. That's not precisely how RSA works, but it's pretty close. So to break RSA, what we have to do is come up with a way of finding the factors of a product without knowing either of the factors first. Okay. The other thing that you need to understand to understand Shor's algorithm is the concept of the period of a function. So on a simple function, like the sine of an angle, which is 2 pi, this is pretty easy to figure out that the period of the sine function is 2 pi. But as a general problem, if I said just give me a function that figures out the period of any general function, that's a much harder problem to solve. Okay. So like many quantum computations, there's both a classical part and a quantum part for Shor's algorithm that are required to get a useful answer. So in essence, Shor's algorithm converts the problem of finding prime factors of a product, which is difficult, into finding the period of a function, which, as I said, for a general function is also difficult. However, finding the period of a function is not hard if you have a quantum computer because of this Fourier transform ability that they have. And the interesting part is it turns out that this actually works, and it's been demonstrated on real quantum hardware that you can use it to figure out the factors of a product. However, the quantum computers that we have today are so small that the products that we're looking at are like 15 and 21. So not useful for breaking encryption today, but still useful in that they show us that the idea is correct, okay? So what we'd like to do is build a larger quantum computer, and we believe that this algorithm will scale in a fundamentally different way than a classical computer scales. So it is impossible today to use a classical computer to figure out the product of, say, 1,000-bit primes. There's too much computation involved in doing that. But if you have a large enough quantum computer, say a few thousand qubits, we think that this can be done efficiently with Shor's algorithm. And the remarkable fact is that it does work. So another algorithm that is useful in a quantum computer is Grover's algorithm. And this is, it works with general functions, not just finding the products of primes. And this is for finding the input to a black box function that returns a particular value. So you pick some value, you want to know what's the input to that function that returns the value. Classically, this is O(n), and Grover's algorithm is O to the square root of n. The Aronson quote is still correct. We're not searching instantaneously by trying all the possible solutions at once, but it is faster than the classical solution of trying them all one at a time. So quantum resistant crypto. So it takes 10 or 15 years, as I said, to gain confidence in a novel crypto system. And then the threat to crypto, and by crypto I mean cryptography, is believed that a quantum computer will break a public key crypto system. We think that symmetric algorithms are quantum resistant already. A number of possibly quantum resistant asymmetric crypto systems are under development and analysis, although some experiments have failed. The GCHQ published a paper called Soliloquy, a cautionary tale, about a candidate crypto system that was a public key crypto system that was believed to be quantum resistant, and then they figured out, actually, no, it isn't. So NIST right now, the National Institute of Science and Technology, has a post-quantum cryptography standardization project where they're trying to come up with a standard similar to how we have AES, which is a standard for symmetric encryption. They're trying to come up with an asymmetric encryption standard that will be quantum resistant. And they had a call for proposals, and 82 serious proposals came in, of which they accepted 69. And by 2019, all but 26 of them were broken or withdrawn. Sometimes they were withdrawn because 2 of them ended up being the same crypto system. Sometimes they were withdrawn because the authors found a weakness in the submission. And on the 22nd of July this year, 2020, 15 of these entered the 3rd round, with 7 that were sort of seeded to be finalists, and then 8 more that were also under consideration. And in 2022, NIST wants to have an initial standard for a quantum resistant asymmetric crypto system, at which point people will continue trying to find weaknesses in it and trying to break it. And hopefully we will get this crypto system finished and people have confidence in it before there is a quantum computer big enough to break RSA or elliptic curve cryptography. So where's my flying car? Like, how close are we to getting this done? Well, let's talk about what that means. So there's this notion of quantum supremacy, which is having a quantum computer that's faster than a classical computer for anything. Google claimed in 2019 that they were able to essentially generate a random number faster than a classical computer. IBM disagreed with them, but it seems like this is going to happen pretty soon if it hasn't happened already. And yet the quantum computations that we're going to be able to do are far, far smaller than are necessary in order to break public key encryption. But that doesn't mean there are no useful things you can do with them. We talked about, combinatorial search problems. That's potentially useful. I think one of the first uses that are going to be a serious use for a quantum computer is going to be simulating quantum physics. That's something that we just can't do now to any big degree with a classical computer, and is really useful in the fields of chemistry and drug research and others. And having a a quantum computer, even if it's not a very big one, the fact that you get a speed up over what you can simulate classically is just immediately useful to you. And then in terms of, saying when can we break encryption? Well, we need to have thousands of entangled logical qubits. That's an engineering problem which could be solved in 5 or 10 years. Maybe it'll take 20, but we do believe it's coming. So I want to just give you some points to read if you want to learn more. There's a blog post here, which is using, I like this post because it's meant for programmers, and it's how to use the Q# language. There's a technical report called Quantum Computing in the NISQ area and beyond that's about 50 pages. It's a very readable summary of sort of where we are today and where we're going in the future. Quantum Computing Since Democritus is a little bit of a harder book. It's about 300 pages, and it's more philosophical in its tone. It talks about sort of what is the meaning of complexity classes like P and NP. And then there's some specific posts that are that there are on some of the topics that I've touched on during the presentation down here on the bottom. And again, if you get the slide deck, you can get links to all these things. And the other thing I want to do is give you a means of contacting me. I'm Craig Stuntz, which is craig.stuntz@improving.com, or Craig Stuntz on Twitter. During normal non-pandemic times, I run a group called Papers We Love, which is for people who enjoy reading theoretical computer science papers, and we meet in Columbus and have lunch and talk over the papers every now and again. And again, speakerdeck.com/Craig Stuntz if you'd like to get a copy of the slides. And I can give this talk or any of my other talks to your team. It's not an ad. I don't charge money for this. I want to build a community which, can talk about theoretical computer science and have fun doing it. So I like to do that. Just reach out and say hello to me and we can talk about it. If you have any questions right now, I'd be happy to take them. And if not, I want to thank you for coming out and coming to the talk today. And I guess I should plug my employer. We're a fun place to work and they support me in doing these presentations. So if this is the sort of thing that you enjoy, reach out to us. And we are hiring in Columbus right now. And we'd be happy to talk to you about that too.